All right. The rest of you that came in, you can get your tests at the end of class. I've got them all done. All the grades have been updated in Blackboard. All the homework has been put in. Remember, every test, I will go back and fill in those homework assignments. So if you didn't do homework assignments from last test, you can still go back and fill those in. It's not the end of the world. We will be, because we didn't have class on Tuesday, I'm not like going to rush through a bunch of stuff because I had a couple extra days play around. So this pushes the test and the review to just after spring break. So we'll finish chapter 7 before spring break, and then you'll have spring break, and then afterwards we'll do the review and then the test for that. So that'll work out fine there. Your projects, I would highly suggest starting to work on your data, trying to find data for your thing, and determining what you want to say about that data. All right. So like, what are you going to try to prove or state with the data that you're collecting? Okay. So I would highly suggest starting to work on that now. If you need help or you have questions or you want to send me your data to look at, you can do that. Okay. We're going to be spending the next few weeks working on probability as part of statistics. So it's not going to be directly related to your projects. After spring break, when we get to chapters 8, 9, that will be more directly related to that. But you can start to collect your data to start doing some of those analyses and the basic calculations, like getting the data in order and finding maybe some nice little graphs and stuff that you can do with it, those type of things. The mean, the mode, the median, standard deviation, those type of things, you can already start to do those calculations. So, all right, probability, chapter 5. First thing we're going to look at is what's known as the law of large numbers. If I ask everybody in here to take out a coin and flip it, okay, would we get exactly 50% heads and 50% tails? No. Okay, we very well could get, let's see, how many ones? About 20 of you in here. We probably could get 15 heads and 5 tails. That would be not out of the realm of possibilities. Okay? Probably wouldn't get 20 heads, but you could. However, the more and more you do, the closer and closer it will get to that 50-50 split that you would expect to have. That's what's known as the law of large numbers. The more you do, the more data and stuff you collect on it, the more experiments you do, the closer it will get to the theoretical probability of what it is. So there's 2 types of probabilities you're going to hear talked about. There is experimental probability and theoretical probability. And I do not know why this book doesn't use those 2 terms. It uses empirical and classical. Don't ask me why. I will explain which ones are which when we get to that in a few minutes. So, yes.
Hey, don't mean to interrupt you, but
sure.
I'm usually in your night class.
Yep.
Do you want me to take the test here or do this class and then take the test?
We'll do the test right after this one.
Okay, just want to make sure.
Yeah.
Okay.
Because I have to print one for you.
Yes.
So you can take this class and then you can take the test and we'll do it afterwards. Yes. All right. So the funny thing about this is I was literally listening to a podcast last night. Neil deGrasse Tyson does a Star Talk podcast, and he had a mathematician on, and they were talking about the law of large numbers and how it relates to the fact that I don't need to interview 350 million people. If I interview a couple thousand, I can get close to that. So that's what the law of large numbers is. The more you do, the closer to the actual probability you're going to get. And it kind of like balances off. Like when you get to like 1,000 coin flips, you're going to get pretty close to that 50-50 split. And doing more is not going to make it much better. And that's where that leveling goes into place. One of the big things whenever we're looking at probability and even when we're looking at statistics, remember the whole concept of random. Okay? A random process represents scenarios where the outcome of a trial is unknown, but the proportion or particular outcome observed approaches a specific value. So we might not know the outcome of any specific event, but we generally will have an idea of what the outcome of the overall event is going to be. So like anytime you flip a coin, you're not going to be able to predict what it comes up to be. If you're going to play roulette and you're spinning the wheel, you're not going to know if it's going to come up black, red, or what number it's going to come out to be. But we have a theoretical idea of what should happen. Okay? So the random process is the flipping of the coin or the spinning of the ball or the rolling of the die. However, we kind of know what the proportion is going to be overall. Probability. It's the measure of the likelihood of a random phenomenon occurring. So whenever we're looking at probability, we're looking at two pieces. We're looking at how many times something happened over how many times that we've done the experiment, if it's experimental, or how many things we want over the total number of possibilities. And that would be the theoretical. So probability typically deals with short-term results. We're going to do a bunch of them. However, based on that, we can make long-term predictions. Just like we've had snow, a ton of snow the past few weeks, and they're talking about another storm next week. The probability is we're going to get it because that's the pattern we're in right now. We're going to get more snow. Not that we want it. We don't want more snow. We have nowhere else to put it. But that seems to be the pattern, and that's weather is like that. They're looking at patterns. They're looking at how things move. However, are they always right? No. Last week's storm, 4 or 5 days out, they didn't know it was going to hit us, and then all of a sudden we got dumped with 20 to 30 inches of snow. So not everything is perfect in probability. There are a couple general rules about probability. The first one, probability can never be negative. It can also never be higher than 1. So it will always be between 0 and 1, or 0 and 100%. If we add up all the possible outcomes, it has to equal 1, or 100%. If the probability is 0, that means that event will never, ever happen. It is impossible to happen. So that'd be like flipping a coin and getting a rabbit. That is impossible. A certain event, if it's 1 or 100%, that means it will always happen. All right, so 0 never happens, 1 always happens. Those are rare. Almost everything in life will never be a 0 or a 1. Because everything can possibly happen once, so it wouldn't be 0. And pretty much nothing ever always happens. All right. I think this is the last of the definitions, pretty much, for right now. We have two different things. We have an experiment. An experiment is what we're running. So as we're talking about flipping a die or flipping a coin or rolling a die, those would be an experiment, how many times I can do it. The sample space is a list of all possible outcomes that I could have. So what are the possible outcomes of rolling a 6-sided die? Yeah. Yeah, that's the sample space. Because those are all the possible outcomes that I can have when I roll a 6-sided die. What is the possible outcomes of flipping a coin? No, what's the sample space? Or heads or tails. Okay, it doesn't necessarily have to be a number. All right, these can be words. So like heads and tails works, or a 0 or a 1 if you want to look at it that way, a binary option. If we're looking at playing cards, you have 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, King, Queen, Ace of 4 different suits. All right, so a sample space is the list of all possible outcomes. The event is what we're looking for in it. So it's a collection of those outcomes. So it is not all of them. It is what happened. So sample space we typically will list as an S, and then the event is an E. It is a capital S to separate it from samples standard deviation, which is a small s. So for example, a sample space we have for the die is 1, 2, 3, 4, 5, 6. The event that they're asking for is rolling an even number. So the event would be a 2, 4, or a 6. The classical probability, as our book calls it, which is known everywhere else as theoretical probability, would be 3 over 6, because these are the even, and that's the total. So it's the number of values in the event over the number of values in the sample space. That's what we have here. So 3 over 6, or 1/2, or 50%. Those are all different ways to label and write probability. What is the, if my event was odd numbers, what would be the list of numbers for the event? What are the odd numbers in a rolling of a die? 1, 3, and 5. So it would also be 50%. Okay. We don't have to necessarily write the event as a list of words. My event can be one number. Like, if my event is rolling the number 1? What's the probability of rolling the number 1? 1 out of 6. Because one in the event, my 6 is my sample space. Those are all what's known as theoretical probability or classical probability, because notice we didn't do an experiment. Okay. If I had you guys all roll a die, and then I counted up how many times 1 came up, or 2, 4, and 6 came up, that would be the experimental probability, or empirical probability, as the book calls it. All right? So if you're physically doing something, that's an experiment. If you're just thinking about what it would be, that's theoretical. Everybody understand the difference between those two? All right. Right from the book on purpose. If it asks you for your probability model, it is just asking you to do the probability of each of the events. So we have our frequency here. We would add them all up, which I probably should have done ahead of time. So that's 200. And then we would divide each of those by 200. So 166. Actually, hold on a second. Not divide them. 0.415, 0.11, 0.05, 0.025. $77, 35, 38.5, or 38, 385. There we go. What did I just do that was on your test? That's relative frequency. Okay? Relative frequency in a probability model or probability is the same. Okay? If you're looking at a table that's a frequency and you're looking for the probability of something happening, that's the exact same thing. All right? Now, in essence, yeah. So, is this experimental or theoretical? This is experimental. Okay? Because they collected the data and they have this information here. All right? However, if we collect enough of this data, we can start to make some observations about what happens in general. So 200 is a good start. All right, we could probably say around 40%, maybe a little higher if people actually do travel or drive alone to work. Okay. Estimate the probability that a randomly selected individual carpools to work. That 0.11. 11%. Would it be unusual to randomly select an individual who walks to work? Based on this data. Yeah, 5%. So walks to work, actually not even 5%, 0.025%. Or 0.025 or 2.5%. There we go. Yeah, that's a very small amount. So yes, it would be unusual to randomly select an individual who walks to work. However, if you did this poll standing downtown in New York, you might get a very different result. Okay, that goes back to how we collect the data. All right. A pair of fair dice is rolled. Fair dice are die where each outcome is equally likely. Compute the probability of rolling a 7. Now, I will tell you that you will see these a lot. I'm going to show you here. It is in chapter 5:1. I have, for those that do not know them off the top of their heads, if in section 3:1 or 5:1, here is all your dice. If you're rolling it twice. And for those who don't know what a deck of playing cards are, here's your deck of playing cards. Okay. I have learned that not everybody actually knows what these things are. So they're on my website. You can easily pull them back up. So it's asking for the probability of rolling a 7, which means we're looking at the sum of these. So if we look at the list, there's 36 total sets of dice. And we want the ones that add up to 7. So 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 1 and 6. So 1, 2, 3, 4, 5, 6 of them. So there's 6 possible outcomes that add to 7. Or 1/6, or 0.167. Was that experimental or theoretical? This is theoretical. These are all the possible ways that I can roll those dice. And I counted up the only ones that are going to give me that sum of 7. What's the probability of rolling snake eyes? And they actually do give you the actual statement of that. It's 2 ones. Or rolling a 2. There's only one. So it's 1 out of 36. So that's that one, and it's 1 out of 36. So is it more likely to roll a 7 or a 2? A 7. So if you go to the casino and you're playing and you watch the game of craps, that's why when you roll a 7, it changes, because 7 is the most likely outcome to get. All right. Suppose you asked 500 families with 3 children, so they are above average, to disclose the gender of their children, and found that 180 of the families had 2 boys and 1 girl. What's the probability of 2 boys and 1 girl in a 3-child family using the empirical method, which is, remember I said, that's experimental. So what's the probability? You can give it to me as a fraction. I don't need it as a decimal. Yep, 180 over 500. Okay. That's experimental because I collected the data to find that answer. Because that's what they told me. It was 180 of them that had it. Now, if we wanted to find the theoretical probability of this happening, I need to create my sample space of all my different options. The easiest way to do this is what's known as a tree. Okay, a tree chart. So my first child, boy or girl. Second child, boy or girl, boy or girl. Third child, you split them up. So we have 3 boys, boy, boy, girl, boy, boy, and so on and so forth. This is no different than if you have flipped a coin 3 times. And we're looking at heads and tails. Okay? So the question was 2 boys and 1 girl. So 2 boys, 1 girl. 2 boys, 1 girl. That's it. Right?
There's 1.
Oh, that one. 2 boys, 1 girl. Okay. Did I get them all now? Yeah. All right. So we've got how many do we want? How many do we circle? 3. And how many total was in the sample space? 8. So that's theoretical, right? And then experimental was, what was it, 180? 180 over 500. Okay, so let's see if they're close enough. This is where dividing and changing it into a percent is nice because we can compare them. Pretty close. 500 is getting up there in the amount of numbers, so that's pretty close to being what we'd expect. If we picked 1,000 families, we'd probably get a lot closer to 37.5%. Everybody get the difference between theoretical and experimental probability? In the end, they're all done the exact same way. It's what you want divided by the total number of outcomes that there happens to be. So now the total number of outcomes will either be your theoretical from your sample space or however many experiments you did. And the top is whatever the piece that you want. Subjective probability, or whatever you think. This is an opinion. Subjective probability is an outcome of probability obtained on the basis of personal judgment. From a statistical point of view, it is worthless. Okay? Great example of this would be Jordan's Furniture. Jordan's Furniture is giving, if the men's and women's basketball team both make the finals in the NCAA tournament, everybody that bought furniture for like a month gets it for free. Okay? That's completely subjective. Now, when he went to the insurance company, because he's not footing the bill for this, he gave him what he thought was a good probability of this. But it was completely based on what they thought. There's no calculation to determine that. Okay? So that's a subjective probability. My guess is there's probably a question in 5.1 that asks you the difference between the three or something in there. Remember, you'll still only have to do 50% of the homework. So. All right. This is where things get a little more tricky. When we're looking at events, not every event is going to be disjointed. Sometimes events are going to overlap. Sometimes two events have nothing in common. Okay? So disjointed or mutually exclusive events would be two events that don't have anything in common. So for example, flipping a coin and rolling a die. Do either one impact the other one? If I flip a coin and then roll a die, do they overlap at all? No. If I take a card out of a deck of playing cards, and then I take another card out of that deck of playing cards, do those two events overlap? Yes, because the first card impacted the odds of the second card. So when we're looking at the next few things that we're going to be looking at, we have to decide if the two events are disjointed or if they overlap and have some interaction between each other, because that's going to change how we do the calculations. If they're disjointed, which means there's nothing, they don't overlap at all, we can just add the probabilities together to get the event, or to get the total probability of those things. So a good example of this I'm giving people a second to finish writing down the formula. Okay. Did you get it all? Okay. Ooh, wrong button. All right, so I've got 3 events. So it's all the numbers from 0 to 10 or 0 to 9. So you'll notice on the outside that little S right there, because this is my sample space. My sample space is the numbers from 0 to 9. We've got 3 events. So E is 0, 1, and 2. G is 5 and 6. And F is 8 and 9. And then there's 3 numbers that are not in any of those events. The 3, the 4, and the 7. So the probability that event E happens is 3, 0, 1, and 2 out of 10, because that's my total sample space. The probability of F happening, there's 2 there, so it's 2 out of 10. And G is also 2 out of 10. Are those events, do they overlap? Or are they mutually exclusive or disjointed? Is there any number that is in 2 different ones? No. So when we're looking at this, we're looking at the numbers inside of it. So it's the 5 and the 6 and the 8 and the 9. So there's no overlap there. So there is no overlap between the circles. So these are disjointed or mutually exclusive events. So if I wanted to find the probability of E, F, or G happening, I would just add those. So 0.3, 0.2, 0.2, which is 0.0 or 0.7. Or if we look at, you can add up the tops. 3 plus 2 plus 2 is 7 over the 10. Huh? Because it was 10 numbers. 0 through 9.
Oh, 0, that's one of the numbers.
Yeah. Yeah, because 0 is right there is one of the numbers.
If the sample space was 10, it would be 11 numbers.
If there was a 10 in there, then yes, there would be 11 numbers. So in this sample space, I've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 numbers. That's why there's a 10 on the bottom. Because I have 10 possible answers. Okay? And then those are numbers outside. Those are numbers that just aren't in E, G, or F. So they're splitting the numbers up. It's totally randomized. It's not any like special thing like with dice or coins or anything like that. They just chose, for E was 0, 1, and 2, for G was 5 and 6, and for F was 8 and 9. And then 3, 4, and 7 are numbers that just weren't picked. So we can look at like you're E, he's G, and she's F. You chose 0, 1, and 2, he chose 5 and 6, and she chose 8 and 9. 3, 4, and 7 weren't picked. That's fine. That's why those are outside. They're not in one of the bubbles. Okay? So that's how we show that would be mutually exclusive. What is the probability of drawing a king? Yes. So we have, those are my kings. So the probability of a king is 4 out of 52. Okay. So we already have the probability of drawing a king. That's 4 out of 52. What's the probability of drawing a queen? Also 4 out of 52, because I have those 4 queens. And the probability of drawing a jack? Also 4 out of 52. What's the probability of drawing a king, queen, or jack? 12 out of 52. So if we do Jack or Queen or King, that would be 12 out of 52. Okay. Why can I just add them? That's okay.
Okay.
Yes, they have the same denominator, so I can't add them and have to actually change anything. That is as crazy as it sounds, that is something that's going to make a difference at some point.
Okay.
Remembering how to add fractions is definitely a skill to remember. Yeah. They all are actually related to a deck of cards, so we can add them. So it's not like it'd be totally separate like a coin or a die thing. Are they mutually exclusive? Or is there overlap between them? There's no overlap. The Jack is a separate event than the Queen is a separate event than the King. Okay, those are completely separate events. So I can add them together to get the total probability of drawing one of those cards. Okay, so they don't overlap each other, so it's fine. So let's see, we've got the probability of a king, which we already did, was 4 out of 52. What's the probability of a diamond? 13 out of 52. So diamonds are these. 4 suits the playing cards, spade, heart, club, diamond. I will highly suggest when you're doing your homework problems for these, if you do not know your deck of playing cards, just go online and find a picture of a deck of playing cards when you're doing them. Okay? I learned the past few years when I've taught this that not everybody knows what a deck of playing cards is. So just look online for a picture of a deck of playing cards. That's why I have them on my website too, so you can easily see what they are there. You do not have to memorize the deck of playing cards. If I gave you a question on a test with this, I'd put a picture of the deck of playing cards on there, so you'll be fine. They might not be color coded though, so you might have to remember which one's red. All right. Probability of a king or a diamond? Yeah. What did we do here when I said or, right? What did we do? We just added them, right? So if we added those, we'd get 17. But are those mutually exclusive events? Nope. The king is here. This one right here overlaps. Okay? That one right there overlaps. These are not mutually exclusive events. These are not disjointed events. We cannot just add these together. Okay? Because they overlap, I have to subtract off that extra piece. So the answer to this question is actually 16 over 52. Because I took the 17 over 52 and I subtracted what? I subtracted that overlap. Okay? There's the formula for this. This is the general addition rule. This actually works for any event. This will even work if they're disjointed. Okay, if the two events aren't connected at all, this will still work. Because if it's disjointed, that right there is always equal to 0. So you would never have to subtract anything because there is no overlap. There is no one where they both occur. So we would add the two events and you subtract off one of the overlaps. Why? I will come back to this page in 1 second. I'm going to go back to the page in 1 second. Don't worry. If you look at this, I counted this king twice. I counted it once here, and I counted it once here. So I have to subtract off one of them. Okay? Because I didn't want to count it twice. That's why that part's there. That's taking away one of the overlaps. Because you didn't want to count it twice. Why what? That was like this, right here. Okay, so if we're looking at just this, right, it's in both. So when I counted it twice. Okay? But that card only appears once. Okay? So I can't count it twice, but if I look at the two individual events, I did count it twice. So I want to cut one of them out so I don't count it twice. That's why I'm taking away that one at the end. Okay? That's what that piece at the end, that P equals E and F. That's the overlap of those two. So here's another example with my nice little Venn diagrams. If you look at E, I've got 1, 2, 3, those 5 events are in E. And then if I look at F, I've got those 5 events. So if we were just adding them and they were disjointed, it'd be 5 plus 5, which is 10, which would equal 1. That doesn't make sense because I have numbers outside. So I know it can't equal 1. So when we look at it, we're going to subtract off those 2 in the middle. Because I don't want to count them twice. Because if you notice, when I did it, I had that one and I had that one. So those right there were counted twice. And I don't want to count them twice. So that's why I subtract off those 2. Because I'm subtracting off those 2, because I counted them in both directions. Okay. The other way you can look at it is, if I'm looking at E or F, I want all those, right? So how many are in there? That's 8. There's your 8 over 10. Okay? So those 2 ways to do it should equal the exact same thing. In this situation, it's really easy to count them and get the answer. It's not always going to be easy just to count them, though. This is known as a contingency table or a two-way table. It does not necessarily have to only be 2 columns. It can be many columns. It can be many rows. What they mean by two-way table is it's relating 2 different categories together. So basically, like your X and your Y are 2 different things that are related to each other. So in this situation, the table has on the top males and females. And then on the left side, never married, married, widowed, divorced, separated. And these are in millions. These type of tables are used a lot, and they will give you a ton of information. reading the questions and answering them is going to be the key piece to this. So the first question says, determine the probability that a random selected U.S. resident 15 years or older is male. So what are we looking for in this table? We're looking for male. So my event is male. So I'm looking for the probability of male. So to do that, I need what two numbers? I need to add up all the males, but I also need all the females too, because that's going to be my bottom number. You don't have to do them separately. So in this, because depending on how many questions they ask you, it might be easier just to do them all and figure it out that way. But for today, you don't have to. And sometimes they're going to give this to you as a frequency or a relative frequency. They're going to give you the percents in them. So the number of males, I have 133.6. Thank you. So the probability of being male, we would divide those. So 49.2%. Yes. Added them all. Yep, it's the total. Sometimes in these tables, they'll give you the total columns, so you don't have to add them all up. They'll be there. This one doesn't. What's the probability of being female? Okay. We'll get to that one in a minute. Yes, 50.8. All right. Determine the probability that a randomly selected U.S. resident 15 years or older is widowed. So now we're looking for widowed. The bottom is still going to be the same. You don't have to add them all back up again. You already have the total. But now we're looking at those two. Okay. Correct. It doesn't say males. It just says widowed. So we're looking for males and females in that category. So 1 or 15? So 5.5%. What's the probability that a random selected U.S. resident 15 years or older is male or widowed? So we had male was 40.498, right? Or 2? Is it 8 or 2? 2. and we had widow was 0.055, right? Because we're going to find, so it's probability of male versus the probability of widow. Do these overlap? Yes. So we have to do the probability of male and widow. We have to subtract that off. So we have, that's the overlap, right? So we had male and widow. So that's the overlap. So I've got to take that away. So I've got to take the 3.5 over 271.7. So I've got to subtract 0.013. Yep. So that's male, that's widow, and that's the and. Hold on, let me do it in a different color. So that's the probability of male, which we did 2 slides ago. That was how. That's that. Huh? You did them separately. We did the probability of male. That was this slide right here. That was the probability of male. Okay? So that's the 0.492. The probability of widow. That we did here. That's that. Now, the probability of male and widow is that 3.5. That's that divided by the 271.7. So right, the total. So that's at 0.013. So that's the male and widow. And then when we put those together, we get 0.534, which is the final answer. So the probability male or widowed is 0.534. Now, you could have, hold on. Good. You could have, just looking at this table right here, added up all the males and added up that 11.5 with it and got the same answer. Okay? Because that would be all the males and then the widows and the females. You could have added those together and got the exact same answer. Because in that way, we would have only counted that 3.5 once. So, but the way we did it, we had done the males, we had done the widows, so we have to subtract off that overlap. Otherwise, we counted it twice. Because that 3.5 is in both of those categories. Okay. Remember I asked you how many females there were? You do not need to add them all up and divide. Okay? The complement of an event is the opposite of that event. Okay? The complement is all the outcomes in the sample space that are not part of that event. So since we figured out the probability of the males was 40.492, the complement to that would be the females. So what we can do is just subtract, because the total's got to add up to 1. So the probability of the female is 1 minus the probability of the males. So it's 1 minus 0.492, which is 0.508. Okay. Sometimes that's easier than going back and doing a bunch of extra stuff. Okay. So if we look at this one, what's the probability that a randomly selected household has earned more than $200,000? So we'd add up all the households. Thank you. You're quick. Huh? Thank you for looking ahead. All right, and then we're going to divide. So that's the total. And we're looking at over 1,500, so 219. So we can divide that. So the probability of being greater than or equal to 200,000 is 0.116. So what's the probability of being less than 200,000? You don't need to go back and add all those up. Okay? That's the complement of this. Yeah. Go ahead. Yep, exactly. So we're going to take 1 minus the probability of being greater than or equal to 200,000. So it's 1 minus 0.116 or 0.884. That's a lot easier than adding all the ones up below 200,000. Okay. That's 5.1 and 5.2. On the website, I have a sample space calculator, so you can actually use this to figure out how many events happen. So if it asks you to figure out how many, like the total amount of things in a sample space, this will do that for you. I've got the coin flips. You can do as many trials as you want, up to 5 trials. It'll show you all the different outcomes there. Dice rolls up to 3. I've got it split, so you can see the first numbers there. And playing cards, you can see the first or a pair of cards. Those sample spaces are there. This here is going to show you, it's a nice little diagram, so you can actually pick. This is my Venn diagram calculator. It'll show you the overlaps in your cards. So like the one we did with the diamonds and the kings. You can see we had that one overlap. So we wanted to subtract that one out. And see, it'll tell you that the events are not disjointed. So I think I only have, yeah, I've got the playing cards and even the nod numbers of playing cards. So this is all playing card stuff. All right. Any other questions? If you came in afterwards and don't have your test, come see me and get your test. You're welcome.